Welcome back to ECE 442-542. We now want to illustrate how we can do this PID controller manipulation of these two real zeros using MATLAB. And what we want to do then is illustrated with these goals. We want to illustrate how we can use rlocus, that function, to actually sketch a root locus plot. rlocfind allows us to actually, with the mouse, figure out what the gain value is at a particular location on our root locus diagram, so we can graphically determine that gain value k versus computing it by hand. And we can also then show how we can transition from our PI control example into the PID controller by using this new function rltool. So we want to first sketch the root locus with the PI controller. Then we will determine the gain, we'll create the closed loop transfer function, and then we will examine the step response of our closed loop system. Then we will do a PID controller using the rltool command. That means that we need to introduce another 0 and the second pole, the pole at the origin, and we'll slide that 0 a little bit off of that pole so that we can hopefully maybe produce a root locus diagram that has our closed loop poles at Z delta locations that are more desirable for percent overshoot, settling time, behavior, etc. We're in both cases with the PI or the PID, because of that integral action, they both better give us and will give us steady state accuracy in the form of 0 error due to a step. So let's now talk a little bit about what commands I've already entered. I've entered the system, that's this unstable first order system, in a MATLAB command, transfer function, and now remember we're entering these polynomials in Z as vectors, as row vectors. And I went ahead and selected a sample period of 100 milliseconds, or that's now consistent with a sampling frequency in hertz of 10 hertz. Here's the nominal transfer function. Notice that I have not yet introduced a k value other than k equal to 1. In this case, k is equal to 1 because it's right there. That's 1 times this z minus 0.988. So I now have a PI controller with a gain of 1, and what I want to do now is go ahead and combine the controller and the plant into a loop gain for the PI controller combination. I'm calling that L gain PI, so loop gain PI controller, and that's what will result. And then I will sketch the root locus, do a root locus find, and then once I've found an acceptable location, I'll plug in the appropriate gain value. I'll change the gain in my loop gain, and then look at what happens in the feedback, closed loop feedback scenario, and that now is consistent with what we've already designed. We have closed loop poles at 0.9 plus and minus j 0.1, and then we can look or examine the step response for that. Finally, after we've done that, we'll transition into a PID controller, and we'll illustrate that by simply putting in the arguments as our system G and our controller C1. That's the nominal PI controller. We'll see that that produces an unstable behavior, so we'll change the gain in that controller to the 1.2002, which is what we needed to stabilize the system. And once we are there, we can now introduce an additional pole and an additional 0 to achieve a PID controller having some structure like indicated here. So I've already introduced this transfer function of a first order unstable system. I've introduced the controller with the same sample period, 0.1. Now what I want to do is actually combine that controller, PI controller, with a gain of 1 with the plant G. So this is now my loop gain with a PI controller. Now what I can do is I can actually look at that root locus of that PI controlled system. So now I'm wanting to have this product of my controller with the plant and sketch the root locus for that. And doing that, I see this particular diagram, but that looks a little bit weird. My unit circle, you can see it's dashed out, but it doesn't look very unit circle-y. So the way that you can improve that, and maybe what I will do is I will make this a little bit larger in terms of filling the screen. And now let me go back. That's looking much better. Let me just go back and say if it didn't look symmetric in terms of the unit circle, you can actually say I want my axis in both the horizontal and vertical direction to be equal. And now I can see, okay, that particular diagram, root locus diagram, you see one branch is blue, and that one's starting at 2 and going and then breaking away a little bit outside the unit circle, coming underneath, and then going to the 0. The green branch is then the second branch. That starts at the pole of our PI controller at z equal to 1 and goes then towards z equal to 2. They hit each other, and then it's the one that's assuming it's going up, and then it zips off to negative infinity. But it doesn't really matter which branch goes where. This is now the structure that we can see for this PI controller. Let's now try to find a gain value using this graphical technique. I'm going to issue the function call rltool with the appropriate loop gain of my PI controlled system. And now when I put my mouse in this diagram, now what I want to do is try to find, roughly split my hash marks vertically so that I'm now between 0 and 0.2 at about 0.1, and try to get that close to the root locus. Now I can hit the left mouse, and where I hit the left mouse is where those red plus signs are. I go back to my MATLAB command window, and I see I wasn't too far away. I now have selected a point that has a gain of 1.211, and we computed earlier that we wanted our gain to be 1.2002, and so I'm actually a little bit further along in my root locus diagram. I'm now at 0.89 instead of 0.9, and I'm vertically a little bit less than at 0.1. I'm at 0.09. But I can now say, you know what, I want to force my gain k to actually be the 1.2002, and that's now going to be the value that I will use to determine my new loop gain. Let me call that loop gain pi2, and that's going to be k times L gain pi. I want to now find the closed loop transfer function for this PI controlled system, and I can do that by forming a feedback path around that loop gain. My loop gain was for the loop gain pi2. I want negative unity output feedback. It assumes negative. I just want unity in the output path, and that's the reason for the 1. And now what I can do is I could either say, what are the poles of that closed loop transfer function? And those are roughly at 0.9 plus and minus j 0.1. But I also now may want to introduce a new figure window and see what the step response of that closed loop system looks like. In doing that, now what I can do is I can see that I've stabilized my system. I commanded the system to go to 1, and indeed it does track and go to 1, but that's a pretty dramatic percent overshoot. I can now right mouse click on this figure window and say, what are the characteristics? What's my peak response? And I can now go and left mouse on that dot and see that I have a percent overshoot of 356 that occurs at 0.8 units of time. And I could also right mouse click and say, oh, what's the settling time? And this is now a 2% settling time, but you can see that the settling time now is 4.88 seconds. That behavior may not be quite what I want. So now what I want to do is say, well, can I improve that by enhancing or making the complexity of my controller a little bit more complex by using a PID controller? So now let me transition from this PI to a PID controller. And the way that I'm going to do that is I'm going to now invoke a new function call, root locus tool or rltool, and let me go ahead and just use the original plant G and the original PI controller with a gain of 1, which I know is not what I want, but let me just do that. And hopefully it will now plot eventually what I need, and look at what happens. I've now generated an unstable response, but if I look at my root locus diagram, those boxes are where my closed loop poles are with a gain of 1. I haven't cranked up my gain enough to move me inside the unit circle, and because of that I can click on this IO transfer function and see that in fact my response is unstable. So now what I want to do is move that closed loop pole, and you could actually, if you saw that hand, you can actually, once it converts to a hand, you can, if I could get it, let me make this window a little bit bigger so that now if I have this hand, I can now move that closed loop pole, if it would allow me, and for some reason I'm having a tough time with my mouse, but you can, if you're not being recorded, I think you can now move that around, and now you can see that I'm able to move that with my hand and get closer to what I want, which is a point, and look at the bottom line. Now I'm at 0.899 plus and minus j 0.09, and once I've now moved my, and that was a gain of 1.2, probably a little bit more. Now I have maybe the original behavior that I had illustrated before, roughly. So now if I say what's my peak response, now I have this percent overshoot above 350. The peak time is at 0.8. My settling time now is going to be roughly the same that it was before at 4.88. Now we may not like that, so now what we want to do is say, you know what, let's see if we can enhance that. We can go into this root locus editor, and actually introduce our pole for the PI controller, which now says that you want to put a pole at the origin. So I'll try to get this at z equal to 0. So I left mouse click that, and this is the resulting root locus diagram with that new pole introduced. That's unacceptable because I'm always unstable, but now I can add in the 0 from my PI controller, and let's put it roughly there. And now it looks a little bit better. Now you can see that my closed loop pole locations are at these square values. So I have two stable poles near z equal to 1, and I have this pole here that's a little bit to the left of the origin. Now, that particular 0, if I move my mouse, it's at about 0.115 now. Let's see what happens when I try to get it about 0.1, and let me see if I can grab this 0. You can see that I now said, oh, if I left mouse click, and now let me put that at 0.9. Now what happens? Well, for the gain so far, you can see that my closed loop poles are outside the unit circle, and I am blowing up in time. But if I now drag these, increase the gain by dragging these poles, I'm still unstable, but now if I move them along, it's maybe a little bit of a challenge to take them apart. So let me grab this one, and now I'm increasing the gain, and now I have stabilized my system. I've moved all three boxes inside the unit circle simultaneously. Let me now grab this one and try to move it, let's say, to 0.7 with a real part, and my imaginary part is roughly at 0.2. And that gives me a damping of 0.7, and I said a sweet spot for damping is 0.7, but here this is a little different because I now have two zeros. For a pure two-pole system, I wouldn't have any zeros. Those zeros actually do deteriorate my step response behavior. But I can now look at that step response behavior, and now look at what I have. Now I've reduced my overshoot from 350 to 120. Maybe that's terrible still, but it's much better than it was. I have a much faster settling time. My settling time before was clear out, well, close to 5. Now it's a little bit beyond 1.5. So now with this particular design, I am maybe a little bit more accepting of the dynamic behavior that I have. And what was my gain at that point? Does it tell me? I'm not sure that it does. So I would have to then determine what is my gain at that point. But I believe if I now go over and say, oh, my controller, now my gain is 1.8846 in this design. My zeros are at 0.9 and 0.09, or roughly 0.1 and 0.9. And if I could actually go in and force this, if I went ahead and introduced, let me just go ahead and do that. I'm going to go up here and edit my architecture, and actually let me go back to my, what was my gain? 1.88. So if I go here and say, let's do C2 is equal to transfer function 1.88 times, and now I want to convolve my two polynomials upstairs. I had one 0 at 0.1, and that's then represented there. I had another 0 that I wanted at 0.9, and that's going to be determined or available by that convolution operation. That's now my numerator. My denominator, I needed a 0 of the denominator polynomial at 0, and I needed another root of that denominator polynomial at z equal to 1. So now, in terms of what I'm trying to do, I'm trying to now produce z times z minus 1, which is z squared minus 1, well, z squared minus z plus 0. If I now put that into a quadratic polynomial, I now have 1 for the z squared coefficient, minus 1 for the z coefficient, and 0 for the other one. I can now go back into my MATLAB window and hopefully type what I just said I needed. I want that to now have a sample period the same. This is now my desired that I want to introduce into my root locus system design tool. So now I'm going to go here and actually say, let me make that C2 and import that. And there is now my controller being previewed, and my dynamic or my root locus shape is very similar to what it was, and the input-output response is consistent with what I would have expected. It's now this 130% overshoot with a peak time at 0.3, a settling time of 1.7, so I'm settling a little bit slower, but now this is for the specific values for my 0 locations at 0.1 and 0.9, and my gain value I could always adjust by dragging this around. I could make this gain value less, and my damping will be worse, and you should now see the result that that produces in my step response behavior. You could even say, well, you know what, let's make this higher gain. I sort of liked that to be higher gain, but look at what's happening with this pole. It's now getting close to the -1, and that's what we may not like. If we crank it up a little bit more, now that pole at -1 gives us this ringing behavior. We still settle, but you may not like this dramatic change up and down, up and down, up and down because of this pole. You say, well, these are better locations for my modes in the positive real axis, but it's now giving rise to this negative pole location. It's stable, but it may not be what we want. So maybe we want to now go back to what we had, but now you can see how you can possibly gain a little bit better insight into why and where you might want to locate your poles based on adjustment of the 0 locations in your PID controller. We could still move those around, but now the gain is at about where we wanted it to be at. The input-output behavior is what we were expecting for those locations. And now if you said, well, maybe if I change this 0, what will that do? Well, now you can see what happens. That now pushed that 0 almost outside the unit circle, and that's what's giving rise to this terrible ringing in your response. So there is some limit to how we can adjust these zeros. It's not trivial to pick a particular value for these zeros, and now using the root locus design tool, or rltool, it gives you a way to obtain insight into this more continual adjustment of zeros in your PID controller to hopefully enhance your performance in the input-output response.